Hello, welcome to the third part of this series about uncertainty. I'm going to be in this part, I'm going to be talking about the propagation of uncertainty. And first, I'm going to talk about very briefly about the concept and the mathematics and the statistics behind that. Then I'm going to continue with giving examples, and each example is going to be slightly more difficult, or it's better to say involved, which is likely to cover, I hope, majority of cases that you are likely to encounter in unit operations laboratory. I will leave the part related with regression analysis and calibration charts later. For this lecture, I'm not going to be talking about that. But other than that, I guess it's going to cover, as I said, most of the, or the majority of the cases that you are likely to encounter. All right, so let's give a start. Okay. So, what is propagation as uncertainty? In a nutshell, the idea is very simple. Up to this point, I have given you some simple examples how to deal with uncertainty. For instance, we measured only mass, we measured only volume, things like that. What if we, for instance, we would like to compute or measure Reynolds number? So you have to compute you have to measure each of the variables in the Reynolds number, like density and viscosity and velocity, average velocity, and what else do we have? Diameter. And then we are going to divide and multiply all of them according to the equation of Reynolds number. So if you commit an error, which you are going to, of course, as accuracy or precision related with some of these variables, how is that error or uncertainty related with that measurement is going to be reflected in the final result? As an example, if you commit, or if there is uncertainty in your velocity measurement, let's say, then how is this going to be reflected in final variance number? So if you look from this perspective, usually we have uncertainty related with very basic measurements, and usually we put those measurements in an equation to obtain another concept, or to obtain another concept quantitatively. So therefore, when up to this point, we just use those point estimates. We just put the point measurement of velocity, density, and other variables, and we find a point estimate of Reynolds number. But just like confidence interval or uncertainty related with each of these measurements, those uncertainty values will also be carried through the calculation, and it should somehow be reflected in the final result. So basically, that's what we are after. So if we call our final variable that we would like to obtain as y, in some cases, we are going to be dealing with only a single measured variable. So this y is going to represent both the final variable or any measured variable. I'll try to show the distinction between those two. The idea is same for two different cases, but I would like to emphasize the distinction between two cases. This is going to be a function of x, and here x would correspond to either variables. So if you have an equation like Reynolds number, then the Reynolds number will depend on density, viscosity, and diameter and velocity. So this is the equation that we have. Or if we are talking about a single measurement, such as, let's say, diameter measurement, right? Then this diameter will be a function of different error sources. So I separate these two cases, but for those two cases, the same logic and rationale and the equation will be valid. And this x, these variables or factors corresponding on which case we are talking about, let's say p variables or factors, using Taylor's expansion and keeping only the first term, this is also called linearization, you can write this y, the measured or computed variable is equal to a y0 value here, right? And around that y0 value, we are going to find the derivative, partial derivative with respect to each factor or variable and multiply by that small perturbation in that variable, and we add them. This is our Taylor's formulation. So this is an approximation for any the actual Taylor's expansion consists of an infinite number of polynomial terms, and the logic is you can approximate or you can write any function using this infinite number of terms of polynomial. But if we have a very small delta x value, so very small perturbation of x around their equilibrium points or measured points, and you can easily say that how are we guaranteed this is going to work for our case, because we assume that uncertainty is small in the measured variables, is small compared to the actual values of the variables. So we hope that this assumption would work. At least we are going to cover the cases for which this assumption will be valid. So in this case, we can write only a single expression like this. And as I said, this is also called linearization because we have now a first order approximation, which is actually linear in terms of x. So if you put y0 here, that we are going to have y minus y0, then the summation here, right, on first order term. Now, if we take the square of both sides and take the expectation operator, this is how you can show it by this way, right? So basically, remember from statistics course, this square here does not mean we first take the expectation and take the square. If you would like to take first the expectation operator, then the square of that, it should have been like that, which indeed we use it. Just a couple of lines. I think somewhere here. Okay, we're gonna come to that. Anyway, so expected value of y minus y0 squared is going to be equal. So it is the difference of y from its y0 value. Do not still, let's not go into uncertainty here. It means that we're going to come to that interpretation in a minute, but it means the change of y from y0 value. It is squared expected value. It may go in both ways, and when you find this the magnitude here and take the squared and take the expected value, you can equate to that term here. So note that this is going to be a constant because y is indeed, think about it as an equation, so its partial derivative will be a single expression. However, this is going to be evaluated at these xg values, right, which are not equal to that xi because it's a partial derivative. I'm not going to go into details about mathematics, but since these are also the equilibrium points, right, each of them is the equilibrium values of xi, therefore this is going to be beta I, a constant, times delta xi squared, and we add all of these terms here. Actually, we first add these terms, then take the square. That's the important point. So if you take the expectation, if you use the expectation operator of something like this, it is very reminiscent of, if you recall, for instance, it's going to be a1 x1 plus a2 x2 plus blah 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 thing. If you recall from statistics course, if you okay, let's put an average square also here. Let's only take two terms. So it's going to be like, or let me write beta 1 and beta 2 so that it's going to be more like to this expression. So there's going to be square here. Then it's going to be beta 1 square, x1 square plus beta 2 square, x2 square plus beta 1, beta 2, x1, x2, 2 with the expectation operator applied in this case. So then you can use the expectation operator to each of these terms. Then, okay, let's get rid of these and come to the original equation. Note that it's going to be the ups. Very same thing here. So therefore, this is going to be each of these terms beta I squared and delta xi squared plus 2 times cross product terms of delta I and delta g with bi and bj terms. So therefore, this is actually, if we call minus y0 as delta x, then expected value of that, I'm sorry, delta y square is going to be equal to this term. And I guess you liken this to something that we have seen in statistics course, which is going to be, this part is going to relate to covariance, things like it. But there's still a couple of more steps. We first note that this expression, expected value of y minus y0 is equal to 0. The reasoning is like this. So y0 is the measured value. Now we should think in terms of uncertainty. Y is the uncertainty here. Uncertain. So it may be in both directions. We would like that. Why is that so? Because delta x is in both directions. So expected value of delta x, for some reason, this e is also, maybe I forgot to write it. So there should be expected value of delta xi, because we assume that x values are again symmetric around a mean value, because we make a very small change. So perturbation in both sides is going to be, is likely to cancel each other. So when you assume this, and note that this is basically, y is a linear combination of symmetric delta x values. Therefore, y is going to be also symmetric. So when you take the expected value, it's going to be equal to 0. Why do we force this? Because we would like our uncertainty estimate as plus minus something. So plus minus something means that the same deviation will be observed for the left-hand side and the right-hand side, because this is very much easy to understand what's going on by this approach. On the other hand, if you would like to be pretty much realistic, and if you take a wider range, right? So if you, for instance, taking higher order terms of Taylor series, then this is going to be, of course, non-symmetric, and this is not going to work, right? So it means that, for instance, such a case here, let's say that this is your measured value y0, and the error distribution is something like this. So in this case, y minus y0 is not going to be equal to 0. On the other hand, when we assume a distribution of this kind, and we assume that we have measured y0 in this fashion, then the right-hand side and the left-hand side fluctuations or dispersion will cancel each other. That's basically the logic there is, and this assumption here make us at the end obtain uncertainty as a plus minus sign. Otherwise, uncertainty will not be symmetric. And for actually more complicated cases, it is not, but we are not going to do those. Anyway, so in this case, delta, if expected value of delta xi is 0, and xi and xj are actually delta xi and delta xj are independent from each other, then in this case, this is going to be 0. Why? Because it's going to be expected value delta xi, expected value of delta xj, and since this is equal to both of them are equal to 0, all the covariance terms will cancel out. If they do not, actually, this is going to be basically covariance of xi and xj, actually, their perturbation values. And here, the right-hand side, this is going to be equal to simply variance of xi, and this is going to be simply equal to variance of delta y. So you may ask, how is this equal to variance? You should remember that variance of x from statistics course, expected value of x squared, the whole square is equal to expected value of x squared. So since this expression is equal to 0 here, right? Therefore, variance itself will be equal to that. Now let's combine. Up to this point, it was statistics. Now let's use this uncertainty. What we call bias square will be equal to this expression here, variance of delta y. And this is going to be, each of these is going to be bias of ith term, x term here. And these are going to be the covariance of ith and jth variable biases. So this is the general formulation for bias square is equal to each bias term is going to be multiplied by the coefficient before that, which is going to be found from partial derivative of y with respect to xi, and then you square them and you add them together. If they're independent, that's the only expression that you need to worry about. If they are not independent, then we are going to also need the covariance term. If I recall correctly, all the examples that I'm going to cover in this lecture is going to be for independent case. We are not going to cover this one. I guess in the next lecture, I'm going to also talking about this part. Anyway, this is how you calculate bias, and I'm going to be using this equation for both cases, as I said before. What are those cases? When the equation, the relation between y and x is in terms of a function like Reynolds number, or we are going to assume that y is a single measurement. And once we find b square, we take b square and we sum it with p square. Remember, p corresponds to precision related uncertainty. It's not exactly equal to precision. Actually, it's the reciprocal of precision. As this p square is larger, it means we have a less precision. But this is the term related with precision, I may say, or the uncertain related with repetition of experiments. So then you take the squares of each of these terms and sum them. This is lowercase u, if you would like to call it. Then you take this lowercase square root of that and multiply with k, which is usually take to be equal to 2. This is going to be our total uncertainty. And previously, I found results omitting this one, for instance, for a single bias term. I actually multiplied by 2. That was the logic. U square in this case was equal to b square. So take the square root, u is equal to b. Therefore, I have written k times b. But if you also have precision, then you have to do this computation. I guess I have given some examples in the previous lecture. Okay, now let's start using this very simple equation. And actually, there are many equations related with uncertainty analysis. All of them are derived using this very simple equation. So you don't need to use anything else. For multiplication rule, for multiplication case, you need some. You don't need a different equation. For addition, you don't need a different equation. If you use this formulation, it's going to always work. In some sources, there are a list of different equations are given. You don't need that. All right. So let's start with the simplest question. We would like to measure of this let's say a single measurement of a liquid, and we would like to give a result for the measured value and also its uncertainty. So what we do is we put this liquid and it reads, actually we read it to be equal to 14.3 milliliters using this graduate cylinder. So what we do is this. We look up, we search for whatever the brand of this graduate cylinder. For instance, you can easily search on internet. Using its specifications, there is usually some information related with accuracy. And this is going to be one of the bias terms. And let's say that the accuracy of the graduate cylinder is plus minus 0.2 milliliters. This is how it's reported in the specifications. Therefore, it is uncertainty is equal to 0.2. Since uncertainty is equal to 2 times measuring manufacturing bias, for this case, it's going to be 2 times BM. So BM is equal to 0.1 milliliters. Now comes the second bias term, which is going to be always resolution. Resolution is 1 milliliter. Let's say here, let's say there is no tick between 14 and 15, so it's going to be 1 milliliter. I'm going to assume normal distribution as I tried to explain in one of the previous lectures. So bias related with resolution is going to be 1/6 milliliters. So the total bias is going to be equal. Now, sorry, let me put before coming to that. It is important, this part. Now you may ask the question, how are we going to find bias? We have now 2 bias terms. How are we going to combine them? Now this equation, note that says y minus yx, or actually simply this left-hand side is going to be a bias term, and this left hand side bias square is equal to each of these other bias terms squared, and also the coefficients are squared. What are the coefficients here? Now let's be careful here. The total bias here is going to be equal to 1 times BR plus 1 times BM, where BR corresponds to resolution and BM corresponds to bias related with manufacturing. You may easily say, okay, why don't we directly use the equation if this is so at 1.1 and 1.6? Note that unfortunately these are statistical quantities. We don't know exactly that they are equal to that value. This is just a random sample from the bias distribution that I tried to explain in the first lecture. But if you know that this is the for any value of BR and BM, if you know these values, the total bias is going to be equal to the addition of those, and the coefficients are going to be equal to 1. So that's my so in this case, what I call is y is this part, and these are going to be my x1 and x2. I'm actually trying to liken this to that equation. So this is the second type of equation that I'm using this method for. For a measured variable, relation between a measured variable and the the factors which cause uncertainty. Therefore, to find B, then it's going to be just BR square plus BM square. This is going to be B square. And where does this equation come from? I'm using these terms. B square is equal to, since these are equal to 1, it's going to be B1 square plus B2 square. And since we have two bias terms here, it's going to be like these. Now we should ask the question, why didn't we take the covariance into consideration? Because we assume that, and it's a very good assumption here, the bias due to production and the bias due to resolution is independent, because the bias due to resolution is due to my eyesight, right? The bias due to manufacturing is whatever the company manufactured, right? And you bought one of these, and whatever that bias is carried here, it has got nothing to do with my eyesight. This is supposed to be eye, by the way. So therefore, the bias stemming from this single observation is going to at least consist of these two components. I say at least because there may be other also bias terms that I have omitted here. So anyway, if you put these values, 1 over 6 here is 1 over 36, 1 over 1.1 is when you take the square, 1, 0, 1. When you add them, you obtain these values. Now note that I have also written the intermediate result. So this 1 over 36 is much larger, not much larger, but slightly larger compared to this value. Therefore, here, if you would like to, for instance, reduce the uncertainty in this experiment, this should be the first part that you should attack, because resolution is a higher contribution to uncertainty here. So when you add them together with square form, we obtain 0.038. So uncertainty, small one, lowercase one, is equal to that one. We take the square root. Therefore, uncertainty here is going to be equal to a bias, or a lowercase uncertainty is equal to 0.194. And to find the total uncertainty, I may say, we multiply it with a we liken it to confidence interval thing, so we multiply it by 2. So now we have 0.4 milliliter. Note that I round off this to 0.4 so that these two decimal points are equal to each other. If you write 34, actually note that this is not going to mean much, because after decimal point, this one has one digit, this one has 2 digits, and when you add them together, only 1 digit will remain. So it is a good idea to keep the significant figures into consideration while also considering the uncertainty. Anyway, Now we have uncertainty value of 0.4. So the result of the measured variable is going to be equal to 14.3 plus minus 0.4 milliliters. Now have an idea about the magnitude of that value. It means this value could be between 13.9, the real value could be between 13.9 and 14.7. And in our to our heuristics about what's going on, I take this value and divide it by measured value to find the percent uncertainty, which is 2.7. That's another way of showing the whole measurement value. So 2.7, you can, depending on the application, it may seem small or it may seem large. But at this point, it seems like it's not a very large value, but for some cases, this may be too large. All right, now let's continue from the previous example and let's make this example slightly more involved. Now, after finding the volume, I would like to determine the mass here in this mass of the liquid in the graduate cylinder. So I put the graduated cylinder here on a laboratory scale balance, and assuming that I have calibrated this lab balance so that when you put the graduated cylinder, it reads exactly 0 here. So I get that uncertainty related with the liquid inside and the graduated cylinder weight, weighing both of them together effect. I neglect that uncertainty. Let's say that I obtain this value, 13.6 grams. Now I would like to determine the density of the liquid and its uncertainty. So now density of the liquid, I have already found volume to be equal to 14.3 milliliters and in the first part. Now I have found mass to be equal to 13.6. So I divide them and with three significant figures, since these are also three significant figures, I find the density to be equal to 151 grams per milliliter. But note that this is a point estimate in terms of statistics I'm talking about, or the way a statistician would call it. So we should also come with a confidence interval, or in measurement theory, I would like to come up with also an uncertainty. So since I have already done the uncertainty calculations related with volume, that's great. I also need the uncertainty calculations for this lab balance. So again, for this brand, I find the specifications, and for this specification, let's say that I find that the accuracy is 2 times 10 to the power minus 3 milligrams. And this is, of course, uncertainty. So the bias stemming from manufacturing is going to be equal to half of that value, which is going to be BM is equal to 10 to the power minus 3, and BM square is 1 times 10 to the power minus 6 milligrams square. And resolution effect, as you can see, there's a single figure here. Therefore, our resolution is 0.1 milligrams. Now, for this case, if you recall, I assume uniform distribution, but because unlike a graduate cylinder, I do not see or and predict where the level stands. So it's totally blind guess. So I assume uniform distribution. So therefore, bias due to resolution is going to be resolution over square root of 12, which is going to be 0.29 grams. So the square of that value is going to be 8.4 10 to the power minus 4 grams square. Note that if you compare those two values, again, this is the dominant uncertainty. Actually, this is much larger compared to this one. It's like, I think, 800 or 850 times larger. Well, this is squared value, so you should take the square root of that value, but still this value is much larger, and it is not surprising. Usually resolution has a higher contribution compared to accuracy if you are not buying some very awfully made or calibrated equipment. Anyway, so B square here is going to be equal to BM square, BR square directly. And where does it come from? Because each of these is going to have a coefficient of 1. And so from now on, you can easily forget about that 1 times BM plus 1 times BR step. You are going to be most of the cases, there may be some cases where you need to use that equation, but you can easily use that squared expression of these two, neglecting the covariance because again resolution and the specification are independent. So B square here is going to be found to be equal to this value, bias of, and this case, let's call it B square weight, related to the weight. And B squared was equal to 0.038 was this value. Where is that? Yeah, that one. If I can find it, yeah, 0.038. And I call it V, that so that it's bias stemming from B. Now, how are these going to be reflected in density? This is the case. Now, when this is the case, I should use this equation. The relation between density and the other terms. So here, bias due to density squared is going to be equal to partial derivative of density with respect to each variable squared and the corresponding bias value. So, okay. So actually, delta rho is going to be rho partial derivative with respect to m. And this is going to be evaluated at the measured conditions. So since density is equal to m over v, this is going to be equal to 1 over v. So this is my partial derivative. And this is the other partial derivative, this time with respect to v squared. And now the important point here is this. When it comes to b squared, I'm going to take the square of those two. I'm going to also have a covariance term. Then the question that you should ask is this one. Is the measurement of m and the measurement of v, are they independent? Actually, with respect to the factors that I have included, think about the specifications here. Specifications are there from different, one is a weighting device, the other one is a volume measuring device. They are totally independent, and the resolution that I read from both devices, they are independent. So we can easily say they are independent from each other. So in this case, our total bias is going to be the square of these two expressions. So I take the square of these expressions. When you take the square of this expression, this actually is going to be equal to bm square, and this is going to be bv square. Or did I call it bw? I forgot. Either m or w. Let's make it m to make it consistent. So this is going to be replaced by this term, and this is going to be replaced by this term. And when it comes to these values, I replace v with the value that I read, which was equal to 14.3. And m and v are also read, so these are replaced by 13.6 and 14.3. And when you do the calculations, I hope I haven't made a mistake, I come up with this value, which is b square. But note that this is bias square. In order to convert, find the uncertainty, I take the square root here, and the total uncertainty here is going to be 2 times b, because there is no repetition of the experiment. There is no term coming from precision. The uncertainty is going to be equal to this term here. Now note that if I repeated the experiment, this value is going to be there would be also a term related with precision. Actually, then it would be b square p square in square root. So one may easily say that, okay, since this would be a positive number, that would have increased uncertainty. So repeating the experiment is not a good thing. Well, indeed, that's not the idea. Here we have not included any random effect here, random error effect here. So when you report this, you are going to say that we conducted the experiment once, and this is the uncertainty value associated with this. And we have no information about the random error due to repetition. So indeed, that's not, so it's not, of course, realistic to assume that if you do not repeat the experiment, then uncertainty is going to be lower. Yes, but as I said, you should also report that you conducted the experiment once. Therefore, this is not an uncertainty which include bias, repetition effects or random errors. So this is not a reliable, let me say, uncertainty estimate. you should usually come up with either using a smart guess or experience or really conducting the experiment. You should usually come up with also a precision value, right? But what I'm doing right now is just trying to show how computations are done. So that's not an issue right now here. So therefore, our result is going to be 951 plus minus 0.029 grams per centimeter cube. Therefore, these are going to be the limits. If you add and subtract these values to get an idea about the width, including also the uncertainty here, you can easily say that just saying 0.95 is not very realistic. Even without random errors, this seems to occupy a pretty much large region. So that's that's one of the very good things about uncertainty analysis. When you do it, and this is actually, as you can see, pretty much theoretical. It's like a back of the envelope calculation. I haven't done anything very serious. I could have very easily come up with those accuracy values related with the specifications of these equipment using the internet, and the other one is related with resolution. So if, for instance, this is a very large uncertainty that you cannot handle, that you cannot tolerate, then you should go back and see which terms I make the most contribution. And here, resolution of both the volume and the mass devices make the most contribution. And let's also compare those two. Which of them is making a larger contribution? This part is a smaller contribution, 10 to the power minus 6, 10 to the power minus 4. Therefore, volume measurement and the resolution of the volume measurement is the bottleneck, seems to be the bottleneck here. That should be better if you would like to decrease this uncertainty. Anyway, finding the percent uncertainty, it is 2.8%. Now, I would like to show you here. Oh, I also made this experiment repeated 3 times. I could have said something about in this lecture. I'm not going to talk about precision, so I will talk about the precision. I actually completely forgot about that. Anyway, now instead of these calculations, note that this equation could have been much longer, consisting of many terms. Is there an easier way of handling these uncertainty calculations? First of all, yes, there are some computer packages. MATLAB also has some packages written for MATLAB, and they are on the internet. You can download them and you can use those packages, or you give the formula and then you give the each of the associated uncertainty values, and it finds the final uncertainty, the total uncertainty, using what we call Monte Carlo simulations and also some other methods. And there is also some computer packages. That's what I was trying to say. For instance, using Python, there are some very nice packages used on Python for uncertainty analysis. Or you may write your own code. The idea is very simple. For instance, for this case, I written this code, and let's see what it does. I called it sim uncertainty kind of thing, and it takes 2 values, volume and measurement point values. So what is the volume that I have measured, and what's the mass that I have measured? So here is the idea. What I do next is just to emulate what's going on here. So what I do is, all right, let's see. For instance, when it comes to volume, it's a little messy, but I guess I'm gonna at least try to handle it. All right. For instance, it says here we have 0.02 accuracy, 0.01 milliliter of bias. So what I do here is, remember, this bias is the standard deviation of a normal distributed random variable. If you go back to the explanation of where that manufacturing bias comes from, so I take a variable and I randomly produce normal distributed 100,000 samples, each of them, and these are sampled from a 0.1 standard deviation. This is exactly what it means. And each of them is going to be a bias term. When it's 0, it is the perfect graduate cylinder. When it is non-zero, some value, let's say 0.2, 0.15, minus 0.1, minus 0.05, whatever, it's that graduate cylinder is going to have the specific bias. And what else? Along with that measurement, there is going to be also a random error due to resolution. And what did I use for random error? I here assume that the random error standard deviation is equal to 1/6, and that's exactly what I do. Again, a normal distribution, distributed random variable, sampled 100,000 times with a standard deviation 1/6. And my volume here is going to be equal to volume plus this specific value plus this specific value. Now you may say that I previously said that these are not added actually, but here note that these are 100,000 different values. So this is the constant V value that I measure. I add 100,000 different combination of these values independent from each other. So I'm going to have 100,000 V values. So it's like I have done this experiment, I have repeated this experiment 100,000 times using different graduate cylinders and using different visual sighting of the level here. But they are indeed all 14.3, the true value is equal to that value, right? But there are going to be some, well, not the true value, the red value is going to be equal to that one, but there are going to be deviations due to those two factors. And I do the same thing for also mass. The value that I measured will be added a manufacturing term. Again, manufacturing error was, okay, let's come to that. So here I have found the standard deviation to be equal to 10 to the power minus 3. So again, the manufacturing bias term is a standard deviation minus 1 times 10 to the power minus 3, right? And when it comes to resolution, there is something else that I did here. I actually note that the resolution is 0.1. Here, since I assume uniform distribution, I assume that any value is sampled between 0 and 0.1. Indeed, I should have, I realized now, subtracted 0.5. Yes, now in this case, the actual value are going to be between minus 0.05 and plus 0.05 with equal probability. So this is going to correspond to my bias due to resolution. So I again add to whatever the value I read, I add these 100,000 independent error terms, and I'm going to have at the end 100,000 M and V. I'm going to divide each of them by the corresponding B term, by the corresponding M, the corresponding B term, and I'm going to be obtaining raw value. And there are going to be 100,000 raw values. So you can easily copy this very simple file, and I hope you get the logic. So let's plot an histogram of raw. Yeah. So under these conditions, if I were to repeat this experiment 100,000 times, that would be the result. So each of them is this like a probability density function, or it is actually an histogram of different values that I'm going to be obtaining. Note that the mode, and this is very much like normal distribution, as you can see, and the mean is around 0.95. Now, what I'm going to do is whether this histogram, this Monte Carlo simulation, fits to what I have found. Here I have found that my uncertainty here, let's see what was the result that I want. Okay, between these two values. And how did I find it? By multiplying by 2, so that it means for 95% of the times, the density value will be in between those two values. Let's see that really whether this is going to work. So what I'm going to do is I'm going to check the raw values. All right, smaller than, what was the value? Let me put it here. 0.9 up to 25. Yeah. So this is going to show how many samples satisfy this condition. And I'm going to divide it by the total number of samples, which is 100,000. All right, so this is slightly below 2%. And let's also find the other value, which is 977. All right, so when I add these values, actually in an ideal condition, both of the values should have been equal to 0.025. So that it would sum up to 5%. But here now it's, well, due to the non-linearity of the process, the result is like 4.7%. So our simplification, note that the simulation was the exact solution, kind of exact solution using our simplification, some of the simplifications or the modeling approach. But the method that I've applied here by using partial derivatives was by using Taylor series first term here. So it was a linearization. So as you can see that linearization and this method works pretty much fine. It's not the exact simulation result, but it is very close. So if you come up with some complex, complicated equation, that's one thing that you may do. You may write the equation here. Note that first you have to define all the biases and add those bias terms to each of these, and you come up with many scalars. So it's going to be long vectors. So then you come up with those vectors which correspond to deviations from the measured values. Then you write your equation relating those variables. There could have been 100 or more variables here, but this method would have always worked because it's, at the end it's going to give you an histogram, and using the histogram you can cut the tails so that 95% or whatever percent that you would like the observations to be trapped in, or let me say confined, you can find those uncertainty values. All right, so let's go one step further and make this calculation slightly more involved. If we repeat this experiment 3 times, note that this was the first experiment that I have conducted, and these are those results, and we conducted this experiment 2 more times. Then let's say that these would be the density values. So we would find the density average, which are going to be these 3 density values, and we would report as our density value. Let's call it density estimate. Now, when it comes to uncertainty here, we also now have some idea about random error terms, about sample preparation, about, I don't know, impurities, about the effect of very short time effects, about my precision as an experimenter, things like that. So what I do is I find the standard deviation here of these 3 resulting values. Note that I do not find the standard deviation here on these variables. I find only the standard deviation on the resulting. We call compute variable that I'm interested in. Then I find the standard, I divide the standard deviation by square root of n to find the standard deviation of the average, which is found here. So what I call p square, so the uncertainty square due to related to precision is going to be equal to the sample variance of density, average density. So I take the average of this value and I find this value. Now U square total uncertainty is going to be equal to B square plus P square. P square is this one. B square is actually we have already computed it, one may say, and I have used this value, the value that we have computed here. Where is that value? B square, yeah, that value. Unfortunately, that's a little bit erroneous because I have to take the partial derivatives now with respect to the average values, which are average density, and it may be average V and average M values. Now that's an important thing. Or in another thing, maybe you may find a partial derivative with respect to each for each case, and that take the average. Now for this case, I will only use this information here. On the other hand, this is if you didn't do something drastically wrong in those experiments, the results would not are not likely to change significantly. But that's the true method. As I said, you should use some kind of averaging here, but I didn't do that. I was too lazy for that. So we have, let's say, this and these terms, and at this point I can still compare those two. As you can see, they are pretty much close. Okay, this says 4, but indeed this is 17.1 10 to the power minus 1. This is 8.28. So this is like 2 times higher than the bias terms, are 2 times higher than precision terms. So it kind of means that you conduct the experiments pretty carefully. And if you would like to really decrease the uncertainty related with density calculations, you should go back and deal with the resolution of the volume equipment, if I recall correctly. So anyway, we take the square, and when we have this one, and we take the square root, and we multiply by 2, and we have this value here, right? And we add this for 0.032. As you can see, 0.032 is slightly higher compared to 0.026, but because now we have also the effects of random error, and now we have 3.4% error. So if we, let's say that, go into the literature and search for a value related with the liquid that we are experimenting with, and we find some benchmark density values, and it says, let's say 0.975 grams per centimeter. Now, and this is the value that we have found. Now, note that if you add this value, 0.032 to 0.951, it's going to be 983. And if you subtract it, it's going to be 990. So the value that I read from the literature, it lies between those two values. It means that, therefore, there is nothing to worry. What does it mean? Let's go a little bit more further. We cannot say that, oh, we made a significant error, there is a significant bias in our experiment. Actually, it is not very realistic to expect something better with this equipment and with this precision. With the things at hand, this error or this difference is pretty much acceptable and should be expected. I should say there is nothing else erroneous in your experiment. Just by these calculations show that. That's kind of not rejecting the null hypothesis, for those who would like to relate this to statistics. In the next lecture, I'm going to be talking about an epic single question.